Thanks for the very nice introduction. But to me, since that so far it seems that I'm the only one who is completely on the application side. I tried to understand all the talks so far, and I couldn't find any talk who solely talking about the performance of specific applications in detail. So today, I will briefly discuss about this nice small experience of the large-scale electronic structure simulation with the MVAPICH, particularly on the Intel night-landing manycore processor. So we are building the in-house code for the large-scale electronic structure simulation. And basically, the purpose of electronic structure simulation is to find the state of electron motion in an electrostatic field created by the stationary nuclei. And it is indeed widely used in very many areas, like physics, chemistry, and material science, electrical engineering, and even for the mechanical engineering. And it has really huge customers in the society of computational science. So this left chart shows the service statistics in North Korea, and which shows like roughly 40% of people uses like quantum simulation represented by electronic structure simulation. And the right chart again shows the service statistics in Korea's supercomputer operated by KIST. It's again roughly 42% of people runs the quantum simulation, again represented by the electronic structure simulation. So the in-house code that we have been built basically solve two partial differential equations coupled loop. The one is the Schrödinger equation, and the other is what is called as the Poisson equation. Both equations involve very large the system matrices, which is called as Hamiltonian and Poisson respectively. And the size of these matrices are exactly proportional to the number of grids in the simulation domain. So numerically, to solve the Schrödinger equations involves a normal eigenvalue problem. And the Poisson equation involves the linear system problem, AX equal B. So the question is, how large are these system matrices? And why do we need to handle these system matrices using high-performance computer? So this shows like conventional nanoscale device image. And this shows like the image of logic transistor. And this shows like the optical devices represented by a quantum dot. And although the core part of these devices is like in just a few nanometers, we need to include the surrounding materials to completely predict the quantum behaviors inside this core channel. So normally, the quantum simulation of physically realizable nanoscale materials and devices involve very large-scale atomic system. And in terms of size, it's roughly a few tenths of nanometers. And for example, if we think about silicon box, whose dimension is roughly 30 cubic nanometer, it already contains about 1 million of atoms. And in the previous slide, I told you the system matrices that we are trying to solve, the size of the system matrices are directly proportional to the number of atoms. And because for my case, I'm using 10 bases to represent a single atom. And if I want to solve like a million atom system, that means I need to solve the 10 million by 10 million matrices, either eigenvalue or AX equal B. That's why we need to parallel computing, because those kind of large matrices cannot be handled in a single PC. So these are some development strategies that we have used. And so to solve these two equations, we use domain decomposition. So let's say this is a sort of the total of the device domain, and along one direction, say x, we use like an MPI-based distributed parallelism. And each decomposes slab and allocated in a single length, then further decomposed in multiple threads. So basically, we are using the hybrid parallelization using MPI and OpenMP. And in terms of matrix decomposition, this all corresponds to the row-wise manner decomposition. So each MPI process has a chunk of rows, as you see from this picture. And each chunk of row then, again, further decomposes to use multiple thread in a row-wise. And this matricized is what's called this tight binding Hamiltonian for the Schrödinger equation. And well, it's a little bit different from conventional finite difference method, which is based on the cubic grid, because all the semiconductor material, most of the semiconductor materials that we are familiar with, like silicon, has like cubic grid, zinc blend or diamond structure. So to solve the Schrödinger equation, we are using what is called the Lanczos method, which is very well-known iterative algorithm to find the eigenvalue of normal eigenvalue problem of symmetry matrices. And as you see from this shows the core of Lanczos loop. And here, what I want to say is it's very simple. What it involves the matrix vector multiplier, right? Then vector dot product. And this is just the multiplication of scalar and vector. And again, vector dot product. And again, the scalar multiplied by vector. So the major two operations that need to be parallelized is matrix vector multiplier and vector dot product. This is what I want to focus. And same for the Schrödinger, same for the Poisson equation. So we have used well-known the conjugate gradient method. And again, the main core loop consists of roughly two major numerical operations. It's again matrix vector multiplier and vector dot product. So as you know, this vector dot product can be performed by calling the MPI reduction, right? The matrix vector multiplier can be, performed by simple parallelization, which can be easily found from textbook. But here, the issue is the matrix is sparse. So we suffer from sort of cache miss compared to the dense matrices. So for example, if we focus on the first row block and vector multiplication, then for example, we first try to multiply this block with x0, then w x1. Then we want to go to x2, but there is no element, right? So suddenly we need to go back to the first component of vector to calculate the second row. That's why we will lose the locality of data, and we'll suffer from the huge cache miss. So basically what I want to say is, the communication pattern happens in 2 points. For the vector dot product, so we have one collective communication. And for this kind of matrix vector multiplier, we need to perform the nearest neighbor communication because we assume nearest neighbor coupling in the matrix. And we have night landing. So I'm pretty sure you guys know very well about these kind of things toward scaling. And this shows some performance results that we have measured in the Intel night landing processors. So we tried to solve some realistic dimension, the silicon phosphorus quantum dot, which is quite popularly researched for the material candidate for the silicon quantum computing. This device corresponds roughly 2 million by 2 million Hamiltonian matrices, and we used 0.7210 and up to 256 cores. And we used the MVAPICH2-2.2 and compared its performance with that measured with the Intel Parallel Studio 2017. So when we do not use the high bandwidth memory, the scalability is not very good, particularly when we use cores more than 32 in a single load. And when we use high bandwidth memory, the scalability becomes good. I mean, up to 64 physical cores. Here so we only use the MPI process. We turned off the thread option. But as you see, MVAPICH compiler to our result. In our result, the MVAPICH compiler shows like a little bit worse communication time compared to that of Intel MPI. Well, this is not real communication time because it is measured in a single load. Maybe it's just time to access the memory, right? This shows like close-up picture of the communication time that measured with respect to the different number of MPI processor. The left picture shows like the case with no HBM, high bandwidth memory, and the right picture shows the case with high bandwidth memory. So again, it shows that the comp time for MVAPICH roughly 2 or 3 times worse than Intel compiler. And I tried to understand, well, although I'm not very familiar with the MPI compiler itself, I tried to understand where this reason is, or where this symptom is coming from. And we tried to draw the 2D map. So this shows the case where we use the total of 64 MPI rank, right? And we draw like 16 by 16 map, right? Because the node that we are using has like 64 physical core, and each core has 4 hardware threads. And we can retrieve the CPU ID, right? So by creating a 16 by 16 map, we try to see, how can I say, which core is mapped to which MPI process, right? So here the black part shows the core or thread where the MPI rank is not mapped at all. And the part with color shows where actually the MPI process is mapped from 1 to 64, which means from the rank 0 to 63. And this is the result in Intel MPI when we didn't use any option. So as you know, let's say this is the quadrant 1, 2, 3, 4, 1, 2, 3, 4. So the CPU group of lowest rank is created in the first quadrant, then the next one is second quadrant, and the next one is third quadrant, and then fourth quadrant. And well, in the previous slide, I told you our application involves nearest neighbor communication, right? So in this case, the communication is quite easy, except in this point, right? So this point, communication is quite nice, but the communication between the second quadrant and third quadrant would be a little bit far in terms of memory access pattern, right? And the third and fourth is also not very bad. But for the case of MVAPICH, when we didn't use any option, well, it's completely random. So do you want to compare these two pictures? So for example, this guy and this guy, like consecutive, this guy and this guy are just MPI process, but it's quite far. So, and because I'm using quadrant mode here, that means, how can I say, this rank to communicate, how can I say, to make the communication between this MPI process and this MPI process. And this process must read their data, some memory here, and need to transfer the data, some memory here, right? Maybe my expression may not completely perfect in terms of computer science terminology, but well, hopefully it's going to make sense to you guys. So compared to this case definitely would need to communication between memory spaces quite far, which is quite far. So this shows some more case. the case of 16 MPI process, and 16 MPI process with the Intel MPI MVAPICH2, and 64 and 64. So, for example, this case, for the case of 16 MPI, the result is quite similar, right? MVAPICH2 shows a completely random displacement of the MPI process, right? In terms of CPU ability. And another issue maybe is the fact that they try to map multiple MPI processes in a single physical core. So in this map, these four 2x2 small box indicate a single physical core, because a single physical core has like the four hardware processes. So because multiple MPI processes map a single physical core, the computational speed might hurt. So in this case, the best alternative for this kind of workload would be like clockwise mapping over MPI process, right? But I didn't figure out how to do it as a compiler option. But it seems that the recently released MVAPICH version now has the CPU affinity, and I really want to try it. Yeah, so how much time do I have? Yeah? Oh, really? Okay. And so maybe you guys may think this kind of things may not be a big deal because I'm sorry. Well, the communication time itself doesn't account much about the total time. But when we use multi-node, the situation is a little bit different. So the multi-node scalability is generally good. Well, this is something that has been measured in three computing nodes, and this is with high bandwidth memory and without high bandwidth memory. Right. And the computation time itself reduced very well, and the problem is communication time. And we really don't know whether this communication time comes from the network speed or intranode memory communication, or how can I say, memory transfer, which could happen due to the CPU opponent that I discussed so far. Okay. So yeah, I will definitely want to dig on more with the new version. And so this is what I have so far. Before closing my talk, I want to thank all the members of the KIST IPCC project, and thank you for listening.